Hi, I'm Rishabh, and today I will tell you about Senate, which is a system that enables multiple data owners to jointly run analytical queries on their collective data without revealing their individual data to each other. And this is joint work with my colleagues at Berkeley and VMware Research. So, a large number of applications and services today can benefit from sharing their data with each other and running joint analytics on their collective data towards a mutually beneficial aim. For instance, in the medical sector, such collaboration can enable healthcare institutions to perform better medical studies. And here's an example of one such analytical query that we drew from the literature. This query aims to find the top 10 diseases contracted by patients who have been infected by a bacteria called C. diff. And in particular, the query can be expressed as a sequence of operations where first, the parties combine their datasets together. They then filter out the rows where C. diff is true. These rows are then grouped together by the type of disease, and the size of each group is counted. And finally, the top 10 groups are identified after sorting them by their counts. Now, the problem with such collaboration, of course, is privacy. Organizations are often unwilling or unable to share their data with each other because the data may be highly confidential, and there may even be laws and regulations that prevent them from sharing their data in the first place. Now, cryptographic protocols for secure multiparty computation, or MPC, promise to enable such scenarios without revealing the parties' data. MPC protocols allow the parties to compute directly on encrypted data and only share encrypted data with each other. MPC protocols guarantee that no party learns any other information beyond the final result of the computation. And in more detail, the threat model for MPC and the desired security guarantees that we are interested in achieving in Senate are as follows. First, each party is allowed to provide its input of choice to the computation that they want to run. Second, from the perspective of an honest party, the protocol should ensure that even if all other parties collude with each other, they should still not be able to learn any information about the honest party's data beyond the final result. And further, the security should hold even if the adversary is malicious. That is, it may deviate from the protocol in arbitrary ways. Now, state-of-the-art protocols for maliciously secure MPC work as follows. Suppose we want to run the SQL query shown on the slide that receives input from 4 parties, where party 1's data is first filtered using a select operation, and then all the parties' data is then joined pairwise. Now, existing MPC protocols require that the entire computation be first represented as a single, large, monolithic circuit, and then all the parties jointly evaluate each and every part of the circuit. So, for instance, all 4 parties in this case will participate in evaluating the select operation, even though it only processes party 1's data. But this monolithic execution is a far cry from how the query would be evaluated if security were not a concern. For instance, this is how natural plaintext computation of the query would work. The select operation would be run locally by party 1 without involving any other party. The next pair of joins would be run by the respective subsets of the parties and therefore could also proceed in parallel. And only the final join operation would involve all the parties. But existing MPC protocols are not able to work this way. They cannot take advantage of parallelism across parties. They can't benefit from offloading a part of the query circuit to local computation. And all parties must be involved in executing the entire circuit. All of this contributes towards the very high performance overhead of these protocols. The question, therefore, is how can we decompose monolithic MPC so as to mimic plaintext execution? Because if we could do so, it would lead to significant gains in performance. And to answer this question, we need to understand why existing protocols require such monolithic computation in the first place, and what are the ways in which things could go wrong if we decompose the computation. So let's take the example of a strawman approach that mimics the execution plan of plaintext computation. The select operation is executed locally as before, and each join operation is a separate MPC computation only involving the respective parties that provide input to the operation. The first problem in this strawman decomposition is that each MPC subcomputation by definition reveals its output to the parties. For example, if party 4 is malicious, it obtains the output of the intermediate join operations MPC, which violates the security guarantee that we wanted, that only the final result of the overall computation be publicly revealed. The second problem in this decomposition is that the adversary can provide invalid results as input to an MPC subcomputation higher up in the plan. For example, if a malicious party 1 executes the select operation incorrectly, it may try to provide the invalid results as input to the next join operation, even though the results might never have been possible had the select operation been executed correctly. And the third problem is that the adversary may attempt to provide inconsistent inputs to two different MPC subcomputations. For example, in this case, party 3 is supposed to provide the same value x3 as input to two different join computations. But if party 3 is malicious, it may cheat by providing different values to the two joins. These three problems are not an issue in monolithic execution and only arise when one attempts to decompose the execution. Our key contribution in Senet, therefore, is the design of an MPC protocol that enables such decomposed execution while overcoming these three challenges. Crucially, not all decompositions are valid, and the decomposition in Senet may be different than the plaintext case. Our protocol thus formalizes the class of decompositions that are in fact valid. As a result, Senet significantly improves the performance of MPC execution while providing the same security guarantees in the presence of malicious adversaries. The parties can now offload some operations to local computation. The execution can be parallelized across parties, and each subcomputation only requires the necessary subset of parties, reducing execution costs tremendously. Overall, Senet makes the following contributions. Senet's MPC decomposition protocol lies at the heart of the system and formalizes several ideas and develops new techniques to achieve its goals. Our protocol is general purpose and may have applications beyond Senet and SQL-based analytics, though it is particularly well suited for the latter. We then turn to the matter of designing efficient circuit representations for SQL operations. In particular, we develop a small set of efficient Boolean circuit primitives and then show how to express higher-level SQL operations as a composition of these primitives. Finally, we put the above pieces together and show how to execute analytical SQL queries using Senet. In doing so, we develop new query planning algorithms that determine how to decompose the query circuit in the best way possible and execute it using Senet's MPC protocol. I will now give you a closer look at how we develop our MPC decomposition protocol. For other aspects of the overall system, please read our paper. So, to understand the steps we take to develop our protocol, let's start with the strawman MPC decomposition that mimics plaintext execution. The first challenge we need to overcome is we want to ensure that intermediate MPC computations do not reveal their output to the parties. And to prevent this leakage, we develop a technique that stitches two different MPC subcomputations together. This approach is called soldering, and the soldering protocol securely transfers the output of one subcomputation to the next without decrypting it, preserving the privacy of the intermediate results. Importantly, our soldering protocol is very lightweight and works even when the parties in the first MPC subcomputation are a subset of the second. The second challenge we need to address is to ensure that the adversary is not able to provide invalid inputs to a parent MPC subcomputation. This means that given a child subcomputation, we need to first be able to deduce what possible outputs are valid. And then the parent MPC must be able to efficiently verify that the received inputs belong to the range of possible values. When is this verification possible in an efficient way? it is possible if each subcomputation in the decomposed version can be efficiently inverted. And we say that a circuit can be admissibly decomposed in a particular way only if every subcomputation is efficiently invertible. Finally, if a party provides the same input to different MPC subcomputations, we need to make sure that the inputs are consistent. For this purpose, we limit the admissible decompositions to tree structures alone and not graphs, which allows us to easily circumvent any potential consistency issues. These three ideas collectively inform the design of Senet's MPC decomposition protocol. And for more details on the protocol's implementation, please see our paper. Let me now give you a glimpse at how Senet improves the performance of MPC compared to monolithic circuit execution. We evaluate the performance of Senet on the TPC-H benchmark, which is an industry-standard benchmark for SQL analytics that comprises 22 complex queries on data split across 8 tables. In our experiments, we assume that each party holds a single table in the benchmark. We compare the performance of Senet against a baseline implementation of the state-of-the-art WRK protocol for monolithic MPC execution, as implemented by the AG-MPC framework. This plot shows the performance gain offered by Senet against the baseline. We find that Senet can support 13 out of the 22 queries, which shows its expressiveness. Further, Senet is up to 145 times faster, bringing MPC deployments for analytics that much closer to being a reality. So in summary, Senet is a platform that enables collaborative execution of SQL-based analytics, even in the presence of malicious adversaries. It significantly improves upon the state-of-the-art by combining a novel protocol for MPC decomposition with efficient query planning algorithms based on a cost model. With that, I will conclude, and thank you for your attention.